So this is a review video for the final exam. I'm going to be going over some problems that cover content from all across the quarter. A lot of it will be focused mainly on content from exam one, and I do have some stuff from like the carbohydrates chapters like that were after exam three. I do touch on the other topics too across exam two and exam three, but if you want more in-depth practice on that, I would watch the other two videos I made. I made a video for exam two review and a video for exam three review. And in those videos, I go more in depth on specific mechanisms, the arrow pushing for that, and more reactions in those two chapters. And so, yeah, if you want more review, go watch those videos. So like this video will kind of be more of a like more diverse spread of topics. Okay, so getting into the first question. So this first question was from exam one, it's version B, question 9D, and it's a nomenclature question. It asks us to name the molecule shown. So the first step is to identify the longest carbon chain. So I'm going to find my longest carbon chain. And so I see that I can highlight it here. It'll be this chain over here where I have 1, 2, 3, 4, 5, 6, 7 carbons. That's my longest carbon chain. And the next step is I need to figure out which way I'm going to number my carbons. So I'm just going to number from top to bottom and bottom to top. And so if I just number my carbons, I can number them 1, 2, 3, 4, 5, 6, 7. Or if I number the other way, I would number 1, 2, 3, 4, 5, 6, 7. And we want the substituents to be on the lowest number carbon. And as I can see here, the substituents would both be on carbon 4, no matter which way you number it. So in this case, it doesn't matter. So either way you number your carbons, you would get your substituent on the same number of carbon. And so in this case, that'd be carbon number 4. Okay, so since I have 7 carbons, the prefix for that parent chain will be hept. And then because I have all single bonds, it's an alkane. My suffix is going to be ane, so it's going to be heptane. That'll be my parent chain name. So the next thing is I'm going to name my functional groups. Sorry, not my functional groups, my substituents. And so the first one I'm going to name is going to be this group right here. And so as we can see, we have 1, 2, 3, 4 carbons. And the 4 carbons are attached in a certain way where we have a quaternary carbon, or we have a carbon that's attached to 4 carbons, but also like the 3 carbons are attached to the same 1 carbon over here. And so the name for this kind of like orientation of 4 carbons is tert butyl. And then other, I'll name my other substituent that's coming off of this one. And so because I like have this carbon that's coming off and also this bromine carbon coming off, what's we're gonna do is we're gonna name this as if we're naming like this new kind of molecule that just looked like this. Like what would it look like? It would just stick it on the front of our parent chain name. So starting with the closest carbon being having like the lowest number. So we would just number this carbon 1, number that one carbon 2. And then on carbon 1, I have a bromine, and so the prefix for that is bromo. So I have 1 bromo. And then since it's 2 carbons, the parent name for that is ethane, and so it'd be 1 bromo ethane, right? But we have to remember that this is not its own molecule. It's a substituent and it's attached to this larger chain. And what carbon is it attached to? It's attached to carbon 4. And so that means we're going to put this in parentheses and put a 4 in front of it. So this will be the name of this entire red molecule over here. And also this tert butyl would have a 4 in front of it too because this tert butyl substituent is placed on carbon number 4. Okay, so now that we have our substituents like named, and we have our parent name, now we have to put the substituents in order alphabetically. And so in this case, you would ignore the tert prefix and you would look at butyl so for the naming. So look at B, and then so it's Bu, and then in bromine, it's in the bromoethane part, it's Br, and so Br comes before Bu, and so our 4,1 bromoethane substituent would come before our 4 tert butyl substituent. And so if we put this name all together, we get 4,1 bromoethane. Sorry, since this is a substituent, it would be ethyl. So 4 bromoethyl, and then we would have 4 tert butyl. And then we would add our parent name onto that, which is heptane. And so that would be the final name of this molecule. Okay. The next question asks is from discussion section worksheet 10. It's question number 4, and it asks us to convert the following sugars that are in Fischer form, so that are in this linear form, to their cyclic form. And so and then it also asks us to identify the sugars as D or L. So there's two ways to do this. You can either do it the long way or you can do it the shortcut way. And so to understand why the shortcut way works, I'm going to show the long method first, like how the reaction mechanism actually works. And I'm going to use 4A as the example here to show you the long way how to do this. Okay, so the thing to know about the Fischer form is that your any of your bonds that are on like the side of the molecule, so like these bonds over here, those will be wedges. And then any of the vertical bonds here will be dashes. And so I'm going to redraw what this molecule would look like if we were to put it into wedge and dash form. So I'm going to keep um the middle ones linear just for like just because it's easy to draw, but these would be dashes. Um so I would draw CHO, and then I would draw a wedge here, a wedge here, so the this, and then I would have more wedges over here. And then wedges over here. And then finally at the bottom, yeah, your CH2OH. So the vertical lines would be wedges, but sorry, would be dashes, but it's easier to just draw a line, so I'm just gonna draw a line. Okay, so the next thing you would do is you would rotate this molecule 90 degrees clockwise. So we're just going to take this molecule that's in its linear form and we're going to basically rotate it on its side. And so when we do that, we're going to get this horizontal looking molecule. And then we're still going to have our wedges in here, but you're going to imagine that you like rotate your molecule. And so all of the wedges that were on like the right side of the molecule are going to become on the bottom side of the molecule. So I'm going to draw that out. And so the next thing you should do you should do this actually at the very beginning. But something that you should always do when you're doing these kinds of problems, you're converting a linear form molecule to a cyclic molecule or a cyclic molecule to a linear molecule, is you should always number your carbons. The reason being is that it's very easy to lose track of which carbon is which. Um, one, because it's like hard to visualize like spatially, and two, also like during exam pressure, you can easily mix up which carbon is which. And so my suggestion, my number one suggestion for these kinds of questions is to always number your carbons. And so the way we number our carbons is that we go from the top down, numbering one, etc. And so this top carbon, which is our aldehyde carbon, is going to be carbon number one. This next center is going to be carbon number two. Next one down is three. Next one down is four. Next one down is five. And then you can't forget about the CH2OH carbon here, which would be number six. And so if I were to match that over here with my rotated molecule, I would have one, two, three, four, five, six. And numbering your carbons is a good way to do a kind of sanity check that you drew your molecule correctly and you didn't flip any OH, H group, or you didn't like drop a carbon accidentally, etc., which is why you should always do it. Okay, so the next thing that we do is that we need to take this fifth carbon over here, and we are going to rotate that fifth carbon one to the right. And so we're going to rotate it one to the right, so that way our OH group is on the left. And so if we do that, what we get is we get our OH group on the left, and then now we have our CH2OH group on this wedge here, and then we have our hydrogen now is on the bottom. And then the rest of our molecule is exactly the same as before, where we have an H, OH, OH, and then on the bottom we have three H's. And so again, number your carbons, make sure you didn't drop anything. Okay? And so what are we doing here? So the way a linear form molecule cyclizes, and this is like the way that carbohydrates cyclize, is that the like one of the oxygens from one of the like alcohol groups that is sticking off attacks the carbonyl carbon in the aldehyde. And so which like matches other reactions that you've seen before in like the aldehyde reaction chapter. And so now what's going to happen is this oxygen's lone pair is going to attack the carbonyl's carbon. So I'm gonna like just draw out um, like the aldehyde, um, just so like you can clearly see what it looks like. And so the lone pair on the oxygen is going to now come around and attack this carbon, pushing off a lone pair from the oxygen. And so when we do this, now we get our cyclic form. And so because there's five carbons, will be five carbons in the main chain plus an oxygen. That's like six atoms in our cycle. So that means we're going to have a hexagon structure. So I'm going to draw it like this. Okay. And the way you number your carbons is you number them, the rightmost one would be number one, and then around. And then you have to remember that like on your fifth carbon, you have this CH2OH group pointing up. So then your CH2OH group points here. And so that's where you would get carbon 6. Okay, now the key thing to know here is that if your wedges are pointing down, that means on the cyclic form, they're going to point down. And then if your wedge is pointing up, then reverse. If your wedge is pointing up, that means that it will point up on the on your cyclic structure. So now we're going to draw this. So we're going to ignore carbon 1 for now. So notice how carbon 1 is our aldehyde carbon. It doesn't have any dash pointing up or down. We're going to ignore that for now. I'm going to come back to that later. But on carbon 2 over here, I have an OH group pointing up. So what does that mean? That means I'm going to draw an OH group sticking up. Carbon 3 has an OH group pointing up. So I'm going to draw an OH group pointing up. Carbon 4 does not have any OH group. So therefore, I'm just gonna put no OH group on it. Okay, now we have to figure out what to do about carbon 1. So carbon 1 has a special name. It's called the anomeric carbon. What does that mean? So the thing about the anomeric carbon is that the resulting OH group can point up or down. And so the reason why it can point up or down is because if we think about the geometry of an aldehyde has the double bond, it's flat, right? So if we have a flat like carbonyl group and our lone pair is attacking that carbon, it can attack from the top or it can attack from the bottom. So the OH group can be on the top or on the bottom, which is why we get the alpha and beta cyclic forms. And so in this first question, it's asking us to draw the beta form. And so you have the beta form, the beta form means that your CH2OH group and your anomeric carbon, which is your C1, point in the same direction, or they are cis to each other. That means that it's the beta form. If they were trans to each other, that would make it the alpha form. And so because the question asks us to draw the beta form of this molecule and our CH2OH group is pointing up, that means that our carbon number 1, our anomeric carbon, is going to have an OH group pointing up. And the reason why, and so I also like skipped the step here where there's like a proton transfer here. I just like fast forwarded the step from like the linear form to the cycle form, but there is a proton transfer in there. That's how you deprotonate the hydrogen on the alcohol, um and then how the oxygen on like the carbonyl gets protonated to like become an alcohol. There's a proton transfer. I just skipped that step, but that is basically how you go from the linear form, the Fisher projection, to the cyclic form. And so the key thing here is number your carbons and remember that your anomeric carbon um, is not carbon 2. Like, so the carbon that ends up right here next to the oxygen, it might look like this carbon over here, but it's not. It's actually going to be your aldehyde carbon. And so it's very important to keep that in mind when you're drawing it, which is why I would suggest to number your carbons 1, 2, 3, 4, 5, 6 to always like be able to keep track of your carbons. Okay. So now I'm going to tell you the shortcut way of how to do this. So now that you know the mechanism, so there's a way you can do these kinds of problems really fast. Um, so I'm going to redraw this molecule over here. So I'm going to redraw 4A. Okay. So we're going to first number our carbons. So number 1, 2, 3, 4, 5, and 6. Okay. So we're going to ignore carbon 5. We're going to ignore the OH group on carbon 5 because remember the OH group that's on carbon 5 is the one that becomes included in the ring, right? So we're going to ignore that OH group. But if you're on your groups on the right side will point down in the ring. Your groups on the left side will point up. Okay. Um, if you have your OH group on the 5th carbon, if C5 or like I'm not gonna call it C5 because sometimes you can have like different lengths of like sugars, right, or whatnot. But if your bottom carbon has the OH group on the right, you're gonna have two things. One, you have a D sugar. Two, your CH2OH group will point up on your ring. Okay? And so, um, and then the final thing to remember is that if you have an alpha form, um, your CH2OH and your C1OH will be cis to each other. Well, sorry, will be trans to each other. And if you have a beta form, your CH2OH and your C1OH will be cis. And the way I like to remember that is that if you imagine like these two groups together, if they're closer together, aka they're on the same side, that means that there's more steric hindrance between them. And that means that like, oh, that's like steric hindrance is a bad thing. And so that would be like the lesser form, which is like the beta form. Versus if they're trans to each other, that's like quote unquote like less steric hindrance. And so therefore it'll be the alpha form. Okay, so now knowing the shortcut way to do it, I'm going to show you how to do the other three parts of this question. So again, the answer to our first question is this is what the cyclic form would look like. And also it is a D sugar since the bottommost chiral carbon is on has an OH group located on the right. Okay, so now I'm going to draw out for B. So I'm gonna redraw the linear form, the Fisher projection. Okay, and it asks us to draw the alpha form. So first things first, number your carbons. So 1, 2, 3, 4, 5, 6 carbons. So I have 6 carbons, so I know that I'm going to have like a hexagon as my ring, so I'm going to draw that out. Okay, and I know that the groups on my right side of the molecule are going to point down, and then my groups on the left side are going to point up. And I know that since my bottommost carbon's OH group is located on the right, not only do we have a D sugar, but also that means our CH2OH group points up. So then now I'm going to number my carbons on like the cyclic form. So we have carbon 1, 2, 3, 4, 5. And then our 6th carbon would be the CH2OH group over here. And it points up because we have a D sugar, and our OH group is located on the right side of our bottommost chiral carbon. Okay, so now we're going to go around, and so for carbon 2, so let's hit carbon 2 first. So in carbon 2, my OH group is on the left, um, meaning that it'll point up, and so the carbon 2 OH group will point up. On carbon 3, the OH group is on the right side, so any OH group on the right side would point down. So in carbon 3, my OH group points down. Carbon 4, my OH group is on the right side, so it will point down. And now we have carbons 2 through 4 labeled. And so now to figure out what's on carbon 1, which is our anomeric carbon, we have to look at what's form, either alpha or beta, that this question is asking us for. And so it's asking us for an alpha form. So the alpha forms means that our CH2OH and our OH group on the anomeric carbon are trans to each other. So since our CH2OH group is pointing up, that means our OH group on the anomeric carbon has to point down in order to be trans. And so that means our OH group on carbon 1 would point down. And once again, because the OH group is located on the right side of our bottommost chiral carbon, that means we have a D sugar. So this is what our cyclic form would look like, and it's also a D sugar. So moving on to the next part. So for C, I'm going to redraw the molecule here. So we have our CHO group on the top. Then we have 4 lines in the middle. And this one asks us to draw the alpha or the beta form. And so first thing we do, number our carbons. I have 1, 2, 3, 4, 5, 6 carbons. And so I'm going to draw a hexagon here. And then I will also number these carbons. So 1, 2, 3, 4, 5. Okay. First off, our OH group on the bottommost chiral carbon is located on the left. So this time on carbon 5, we are going to draw our CH2OH group pointing down. Okay. And then remember that any OH, the OH groups on the other carbons, that other chiral carbons that are on the right side will point down. On the left side, they'll point up. And so if we look at carbon 2, our OH group is on the right, so it's going to be drawn downwards. Carbon 3, our OH group is also on the right, so it's going to point down. Carbon 4, our OH group is on the left, so it's going to point up. Okay, and now we look at, to figure out what direction the OH group points on carbon 1, we have to look at the alpha and beta form. And so because it's asking us to draw either, the way we denote that is we draw a squiggly line. And so you just draw a squiggly line, and that will represent the bond, and you just draw it like straight horizontal, OH. And so that is what like alpha or beta form means. Um, if you were to draw the alpha form, or like just the alpha form, I can draw out what that would look like. So I'm going to redraw the molecule over here. So alpha form means that your CH2OH group and your OH group are trans to each other. So since our CH2OH group is pointing down, that means our OH group on the carbon 1 would point up. And then the beta form, I'm going to redraw the molecule again. So OH, OH. In the beta form, your CH2OH group and your OH group are cis to each other. And so that means that your OH group would point down on carbon 1 since your CH2OH group also points down. And so that is how you do 4C. And then last but not least, 4D. I'm going to redraw what 4D looks like. So we have our aldehyde carbon here, and then now we have 3 chiral carbons in the center. And then this one asks us to draw the beta form. Okay, so first thing we do is number our carbons. So our aldehyde carbon is number 1, and then going down 2, 3, 4, 5. And so 5 carbons, and so that means like 4 of those carbons plus an oxygen will be in a ring, and so I'm going to draw a pentagon instead of a hexagon this time. And I'm going to number my carbons again. So 1, 2, 3, 4. Okay. Our OH group on our bottommost chiral carbon is located on the right, so that means it will point up on our ring. And so that means on carbon 4, I can draw pointing up our CH2OH group. That is carbon number 5. Carbon number 2, our OH group here is located on the right, and we know that molecules on the right are located down, molecules on the left are located up. And so that means that carbon 2, our OH group will be down, carbon 3, our OH group will be up. And now we have to figure out anomeric carbon, if it's up or down. And so since we're drawing the beta form, that means our CH2OH and our OH group are cis to each other, meaning that since our CH2OH group is pointing up, our OH group will also be pointing up like that. And again, to determine if this is a D or an L sugar, our OH group is on the right, and so that means it'll be a D sugar. And then for part C, I believe I forgot to include whether or not it was a D or L sugar, but since our OH group is on our bottommost chiral carbon is located on the left, that means we have an L sugar. And that is how you convert the Fischer form to a cyclic form for carbohydrates. So this next question asks you to draw glucose in its like ring form in the Haworth projection, and ask you to draw the alpha or the beta forms of glucose. And so, um, in order to like, so with glucose, they don't give you the structure here, but you could just like look up the like structure of glucose. Like I don't believe in this class we ask you to memorize any structures of any carbohydrates. Um, but I'm going to draw out the where the OH groups are to like make it a glucose molecule, and then I'm going to leave the anomeric carbon blank so I can show you how to determine if it's um, alpha glucose or beta glucose. So glucose um, looks like this. So I'm going to draw two of them. And so if we like say our CH2, OH group is pointing up, and then down, down, this one's up. Okay. Because remember the way we determine if our Haworth projection is in the alpha or in the cis form depends on your anomeric carbons OH, whether or not it's cis or trans to the CH2OH group. And so um, if our CH2OH group and our C1OH group are trans, that means we have the alpha form. If our CH2OH group and our first carbon's OH group are cis to each other, then we have the beta form. So in order to draw the alpha form, I need to draw my OH group in the trans orientation from the CH2OH group. So that means my OH group would point down since my CH2OH group is pointing up, and that would be alpha glucose. And then for the other molecule of glucose that we want the beta form, we want the CH2OH group and the OH group to be cis to each other. And so since our CH2OH group is pointing up, our OH group will also point up, and that will be beta glucose. So these would be the two structures of glucose that you would draw in this question. Okay. Now moving on to the next question. It's from discussion section. It's worksheet 10, question number 5. Now we're going the opposite direction. So the question asks us to convert the cyclic forms, like the Haworth projections, to the Fisher form, and then to also identify the properties of the sugar, such as whether it is D or L, or whether it's a D or an L sugar, or if it's in alpha or beta sugar, or alpha or like an alpha beta form. And so the way you do this is first, let's identify like the alpha beta form, right? Because um the way you do that is looking to see if your CH2OH, if you're like your CH2OH group on your bottommost chiral carbon and your OH group, sorry, and your OH group on the on your anomeric carbon, it are like cis or trans, right? So first I'm going to number the carbons around. So 1, 2, 3, 4, 5, right? Okay. And then so my CH2OH group and my OH group are cis to each other. So these two are cis. So therefore I have a beta form. Okay? Now to identify whether or not this is a D or an L sugar, I look at to see is my CH2OH group pointed up or down. So since my CH2OH group is pointing up, that means I have a D sugar. Now let's move on to the next one. So I'm going to number my carbons. Okay, so is my CH2OH group and my OH group on my anomeric carbon or carbon 1, are they cis or trans to each other? They are trans to each other, meaning that I have an alpha form carbohydrate. And then the next thing to look at is where is my CH2OH group pointed? Is it pointed up or down? It's pointed down. Therefore, I have an L sugar. On my last one, I'm going to number the carbons again. And so I'll just number 1, 2, 3, 4, 5, 6. And so carbon 2 is our anomeric carbon. Um, and so like you have to remember that like just because you have like a carbon number like one, that doesn't necessarily mean it's like your anomeric carbon because in this case the Fisher form will like have a ketone, which I'll show you like later how um like how do you know that it's a ketone, but basically it's because you have one carbon that's bonded to a CH2OH group and an OH group instead of a hydrogen. And so we're comparing C2 versus C6 now. And so if we look at our CH2OH group and our OH group on our anomeric carbon, are they cis or trans to each other? They're trans, therefore we have um, an alpha form sugar. And the next thing to look at is the location of this CH2OH group. Since it's pointing up, that means we have a D sugar. So that's how you very quickly identify if you have a D or an L sugar, or if you have like an alpha or beta form. Um, yes. Okay. So now we're going to convert each of them to their Fisher forms. Okay. So the next thing that we're going to do is we're going to convert them into their linear forms. And so if we take the first one, uh, we see that we have 5 carbons, right? And we also know that since we have a carbon that's bonded to a CH2OH group and a hydrogen, instead of another OH group, we have an aldose. And so because of that, um, um, we're going to, or sorry, not that we have, not on our fourth, and look at your anomeric carbon. In this case, on your anomeric carbon, your carbon is just bonded to an OH instead of another like CH2 OH group. And so because of that, you have an aldose. And so we're going to draw 5 carbons with an aldehyde at the end. So CHO, and then so that's carbon 1, 2, 3, 4. And then 5 would be our CH2OH. So if I number my carbons, I have 1, 2, 3, 4, 5. Okay. And then you have to remember if your OH group is pointing down, that means it's on the right side. If it's pointing up, it's on the left. And so since on carbon 2, our OH group is pointing down, that means it will be located on the right. And then on carbon 3, our OH group is also pointing down, so we were located on the right. And then since our CH2OH group is pointing up, that means it's a D sugar. And for D sugars, our OH group on the bottommost chiral carbon will be located on the right. And so that means our OH group would be pointing on the right there. And so that would be the linear form for there. The second molecule, we have 1, 2, 3, 4, 5, 6 carbons. And since our anomeric carbon is bonded to only an OH instead of an OH and like a CH2 OH group or whatnot, that means we have an aldose and it's 6 carbons long. So that's carbon 1, and then 2, 3, 4, 5, and then 6 would be our CH2OH at the bottom. So I'm going to number those. Okay. So then for carbons 2 through 4, we're going to look at the location of the OH, whether it's pointed up or down, and then based on that, draw our OH group on the right or left. So on carbon 2, our OH group is pointing up, which means it goes on the left. On carbon 3, our OH group is pointing down, so it goes on the right. On carbon 4, our OH group is pointing down, so it goes on the right. And then finally, since we have an L sugar, that means our OH group on our bottommost chiral carbon will be located on the left. Okay, finally for our last molecule, so we have a ketone, and we know this because our anomeric carbon, which is number 2, is bonded to an OH group, and instead of being bonded to an H, it's bonded to another CH2 OH group. And so I know that I'm gonna have like a 6 carbon chain, but the second carbon is going to be a ketone. And so if I draw my first carbon over here, so CH2OH, that's carbon one, and then my carbon two is gonna be a ketone, and then carbon three, four, five, and then carbon six would be my second CH2OH group. And then similar process to last time on carbon, I'm going to number my carbons. So one, two, three, four, five, six. And so on carbon three, my OH group is pointing down, meaning that my OH group will be located on the right. On carbon four, the OH group is pointing up, so my OH group will be located on the left. And finally, on the bottommost chiral carbon on carbon number five, my CH2OH group is pointing up. So since it's pointing up, that means it's a D sugar. And if it's a D sugar, our OH group on our bottommost chiral carbon is going to be located on the right. So this is what the molecule would look like for 5C. And that is how you convert a cyclic sugar in a Haworth projection to the Fisher form, which is the linear form. Okay, so this next question is from exam 1, version B. It's question 12D. And so it gives you a molecule and it asks which molecule represents the enantiomer of molecule E. And it says to select all that apply. Okay, so I'm going to use molecule F as an example first. Um, but there's two ways to do these kinds of problems if you have a chiral center. So this center is chiral because you have four different substituents bonded to it. And so it's chiral. Um, and there's two different ways you can do this. Either you can assign RS chirality to figure out if the molecule is the same or an enantiomer, or you can rotate the molecule and figure out like spatially whether or not it's the same molecule or not. So um, I'm going to show you how to rotate this molecule first. And then inevitably using RS chirality is kind of like a good sanity check to like systematically check whether or not two molecules are enantiomers or diastereomers or the same or not. Um, we don't test or we don't like ask you to label chiral centers RS in this class, but I think that knowing how to label chiral centers in RS makes these kinds of problems much easier, just because sometimes it can be hard to like flip molecules around. And so the way you would do this is I'm going to try to get molecule F to uh, look like um, molecule E. Okay, actually, sorry, I meant to say that I would show how, not molecule F, but molecule G looks like molecule E because like you can rotate molecule G to look like molecule E. But so if this is your chiral center, like this blue star over here, um, I want to like see if it's possible to rotate molecule G around this chiral center to see if I can get it in the same orientation as molecule E. So the way you do this is you're gonna have to rotate the molecule. And so if you have a model kit, I would suggest like using that to help you visualize it, or there's like online different like websites that have like 3D models of molecules. Um, but like on an exam, if you're not allowed to have any of that, I would suggest like using your fingers. So I use my like in this case, I'll use my left hand, and I imagine that like my palm of my hand is my carbon, and then like these three like my three fingers sticking out right here are going to be each of my substituents. And so um I'm going to let's like I'm gonna like hold it up against myself. So I would suggest like you can also like hold up your fingers to look at yourself. So I would use your left hand. Imagine your palm is your carbon, and imagine like your thumb in this case would be whatever is pointing in the front. And so in this case, my thumb would be my methyl group because my methyl group is located on the wedge. My middle finger pointing in the back would be my ethyl group because it's pointing in the back, and my in plane in plain like substituent, which is my pointer finger, would be my I group because it's in plane. So now I want to see what happens to like the other groups if I want to try and get my I want to try to get my I group, which is in plane, to be in the front. So what I want to see is if molecule G, I can make it look like molecule E. So I'm going to do is I'm going to draw the base here. I want to see like except I'm not going to draw like what's after. So this is like my chiral center, right? And so I want to see what happens if I push my I group in that's like in plane if I push it to the front, which is my thumb. So I'm going to draw my I group just like in plane right now. Okay. And so I'm going to make my I group in plane. So watch this. If I make my I group go in plane, I'm going to rotate my fingers like towards me. So if I'm gonna rotate it towards me, my pointer finger replaces where my thumb was. So I'm gonna do that one more time. So my pointer finger, which represents my I group, is in plane right now. It's like it's in plane. Now I'm going to rotate it so that it's pointing forward. And so it's gonna replace where my thumb was. So I'm going to have to rotate it this way. Okay, so now we need to figure out if my pointer finger is now in the front, what happened to my other two groups, right? So what I noticed is that my thumb now, instead of being in the front, my thumb is in the back. So what group was my thumb? So if I go back to my original structure, my thumb was whatever was located in the front. That's my methyl group. But then if I rotate to make the I group become forward, that pushes my methyl group to the back. So now I know my methyl group, which is my thumb, is in the back. And so now I'm going to draw my methyl group in the back. And therefore, what does that leave left to be my remaining in plane group? That's my ethyl group, right? And so, and I can also like prove it to you now here. So my ethyl group originally was in the back, so that's my middle finger. If I rotate my pointer finger to replace where my thumb was, I rotate it like this. And now if you notice, my pointer finger is, sorry, my middle finger is in plane. Okay. And so that's how you know that molecule G is actually the same as molecule E. So therefore, molecule G and molecule E are not enantiomers. They're the same molecule. Except rotating the molecule is kind of tricky and it's still a skill you should know how to do because the RS chirality trick doesn't work unless you have a chiral center. But another way to do this is to assign R and S chirality. So the way you do this is the first thing is that you need your so first assign priority to your groups. So how do you assign priority? So from the car, so the highest priority group, or it's referred to as highest priority, is the group with like the highest like atomic number. So in this case, like hydrogen, because it has the atomic number of one, will always be a lowest priority group no matter what. And then if your groups like going out from the chiral carbon are both the same molecule, like same atom, then you go to the next atom after that. And you go to the next atom after that to see until you have like a differentiating like point of next atom of comparison. So if we were to do that for this molecule over here, right, molecule E, if we were to assign priority, we have a carbon and we have carbon and we have a carbon and we have carbon. We have four carbons, okay? So that's like the same everywhere, right? So then now we have to go to the next atom out. So after this carbon, we have an H, okay? So now we're comparing an H and then another C. I'm going to do this in a different color so it's easier to visualize. So after this carbon, we have an H. After this carbon, we have carbon, another carbon. After this carbon, we have another carbon. And after this carbon, we have an I. So I is like has a way higher atomic number than C or H, right? So that means I like this substituent would have priority number one. H has a lower atomic number than like anything else, which means that H would have like this methyl group would now have be the lowest priority. So we're going to assign it number four. Now we would continue on looking at the bottom two. So on the left side, our next atom is a carbon, but on our right side, our next atom is an H. And so C has higher priority than H, and so therefore our Propyl group will have the priority number 2, and our ethyl group will have a priority number 3. So now we assigned highest to lowest priority. Now, the next thing you have to do in order to assign R and S is that you need to have your lowest priority group either be a dash or a wedge. So you need your priority group number 4 to be either in the front or the back. And so in this case, it's in the back, so we're good. We don't have to do any rotation. If it was located in plane, you would have to rotate the chiral center so that your lowest substituent group is either in the front or the back. The next thing you do is you're going to draw an arrow. So you're going to draw an arrow connecting 1, 2, 3 in that order, from highest priority to lowest priority. So in this case, I have 1, 2, 3 here. So I'm going to draw an arrow connecting them. And then you're going to see which direction that arrow goes. So this arrow goes to the left, which is counterclockwise. Okay. And then my lowest priority group is in the back. So if you go counterclockwise and your lowest priority group is in the back, that means your the chirality you would assign that center is S. Okay? So I'm just gonna like write a quick like cheat sheet for like how to assign like RS. So um if if you are going um if your lowest priority group is in the back, so AKA it's like it's on a wedge, that means if your numbers 1, 2, 3 connect clockwise, then that means your the chirality will be R. And then if your 1, 2, 3 is going counterclockwise, then you would have an S chirality. If your lowest substituent group is in the front, aka you have a wedge, then the counterclockwise clockwise becomes flipped. So if you have clockwise, you're going to have an S chirality. If you have counterclockwise, you're going to have an R chirality. Okay, so the way I like to remember this is that I just pick one of these to remember. So either pick the lowest substituent in the back to remember, or pick having the lowest substituent in the front to remember. So I like to remember the one in the back. So I like to think that having a low substituent in the back is better because you want the low substituent thing in the back. You don't want something that's a low substituent to be in the front. So if we want it in the back. And so if we're going clockwise, we're going to the right direction. And if we're going right, right starts with the letter R, therefore the chirality will be R. And therefore counterclockwise, which is like the wrong direction, like just the opposite direction would be the other letter, which is S. And then with that way, I remember that like, okay, if my lowest substituent is put in the front, it's on a wedge, that means that normally clockwise would be an R. But since I have my lowest substituent thing in the front, which is wrong, that means that I flipped the letter. So it's actually an S. So that's how you assign chirality. And so if we go back to molecule G, we're going to assign like the chiral center, like what is its chirality. And so if I assign priority, the I group would be priority 1, my propyl group would be number 2, ethyl group number 3. And so I'm going clockwise, but also my lowest substituent thing is in the front. So normally if you have clockwise, it'd be R, but if my lowest thing is in the front, that means it's actually S. So this chiral center is S. And so since my chiral centers are the same chirality, E is S and G is S, that means that it's the same molecule. I can do the same for molecule F. I can assign chirality. So then let's look at assigning their highest priority is our I group, second is our propyl group, our third is our ethyl group. If I draw my direction, I'm going counterclockwise. Normally counterclockwise would be S, but my lowest substituent group is located in the front. Therefore, the S gets converted to an R. So now I have S as a chiral center for molecule E, R as a chiral center for molecule F. And so since it's S and R, since it's flipped, that means molecule F is an enantiomer. So I'm going to check that off, molecule F as being an enantiomer. Okay. Molecule H is a little different, right? Because our lowest priority group, which is our methyl group, is not located on a dash or a wedge, meaning that we can assign chiral centers. So we need to rotate this molecule so that our chiral center has the methyl group either on a dash or on a wedge, which is why it's still kind of an important skill for you to understand like how do you rotate molecules. And so if I just like imagine I like have my fingers like this and I like rotate it like that to like try and get like um the methyl group either be in the front or the back, what ends up happening is that if I rotate to the right, my methyl group ends up on the front. My the group that was in the front now ends up in the back, and the group that was in the back now ends up in plane. So now I'm going to assign priorities again. So my I is priority one, my propyl group is priority two, and then my ethyl group is priority three. I'm going to draw arrows connecting one, two, three. And so I go counterclockwise. And so counterclockwise is normally S, but since my lowest priority group, which is my methyl group, is in the front, I'm going to flip that S to an R. And so molecule H also has chirality R, making it opposite of the chirality of the chiral center of molecule E, making it also an enantiomer. So the answer to this question, which molecules represent the enantiomer of molecule E? It's molecule F and molecule H. And so that is how you would do these types of questions. So my tip for you would be to assign RS chirality. It's like a systematic way to be able to check like whether or not you have the same molecule enantiomers or diastereomers. It's just that you have to make sure um, you remember like this chart correctly and that you know how to correctly assign priority to different groups. Okay. The next question asks us to list the molecular formula for these alkane molecules. And so the way I would do these questions is I would always make sure to draw out the hydrogens on each of these molecules. And so we can do that with the first one. So if we have H's here, we have H's here, there's an H here, here. So basically, I'm drawing all the implied H's, and the way you know if there's an H there or not is that if you have a carbon, carbons are bonded to four things if they're in or neutral state. So if they're bonded, if they have two lines on them, for example, that means they need to bond to two other things. In this case, they're just hydrogens. Okay, so now that I draw all my hydrogens, I'm going to count the number of carbons and the number of hydrogens. So the number of carbons is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 carbons, so C9. And then I'm going to count the number of H's. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have C9H18. Okay, moving on to the next one. So they already drew out all the hydrogens for you, which is great. So all you need to do is count them. And so the number of carbons is 1, 2, 3, 4, 5. So I have 5 carbons. And then if I count the number of hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So then it would be C5H12. The next one, I'm going to draw out all my hydrogens again. So my tip for these kinds of questions would be to always just draw out all your hydrogens. That way you are less likely to like miscount them or like forget that a hydrogen was there. So if I count the number of carbons, I have 1, 2, 3, 4, 5, 6. So it's C6. And then I count the number of hydrogens. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's C6H14. And then last but not least, last one. Um, so I'm just gonna write like CH3s on like these end ones just so that I don't have to draw out each individual hydrogen. And then there's H's here, 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 and then there's 2 hydrogens on each of these carbons. Okay, so now I'm going to count my number of carbons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So C16. And then the number of hydrogens I have are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So H34. And that is how you figure out the molecular formula for these alkane molecules. So the key thing to remember here is that just remember that carbon in its neutrally bound, its neutral state is bonded to 4 different things. So if you see it bonded to 2 things, that means that the other 2 things that it's bonded to are not drawn, which are your hydrogen molecules. And so then from there, my tip would be to draw the hydrogen molecules so that you can't miscount them. And then from there, it's just like checking your work to make sure that you didn't like miss anything when you counted. Okay, the next question asks you to draw resonance structures. So it asks you to draw the flow of electrons from the left-hand structure that would result in the right-hand structure. It basically asks you to like draw the arrows, like how would arrows push? So you have to remember that arrows, the start base of an arrow starts from a source of electrons. So you can either start from a lone pair or a bond, and then direction that it goes is it can either go to an atom or a bond. And so in the first one, I see that I'm basically shifting where my lone pair is from one oxygen to the other. So in order to do this, I'm moving my lone pair in. I push it to this bond here, and then I push this bond up here. And so we have to remember that, like, you can imagine a bond contains like 2 electrons. So that is why you end up like, even though you start from one bond, you end up with like a lone pair of electrons, 2 electrons. The next one over here, we're just like shifting the location of the bonds. So I would just push the arrows here. And then the last one, I can see that I have a double bond here, but then now I have a lone pair. So that means that instead of being shared between the oxygen and the carbon, instead it just ends up as a lone pair on the oxygen. So then I would just take my arrow, start it from the double bond, and draw it to the oxygen. And that's how my bond ends up as a lone pair. And then because carbons are bonded to 4 different things, if I remove a bond from it, that leaves behind a positive charge. So it's also important to like make sure you like draw that positive charge. Having that positive charge is also a sign that indicates that something has to leave that carbon in order to make it have a positive charge. So your arrow should probably start from a bond that is next to like attached to that carbon. And so that is how you draw the resonance structures, or that's how you draw the arrows to show the flow of electrons between these resonance structures. So this next question asks you to rank the acidity of carboxylic acids based on the given pKa values for these carboxylic acids. And so if they give you the pKa value, the way you rank acidity is just like a lower pKa equals more acidic. So if we rank them from most acidic to least, we just like compare these numbers. And so the lower the pKa, the more acidic it is. And so then it would be C is more acidic than B is more acidic than A is more acidic than D. But let's say you weren't given the pKa's, how would you figure out like whether or not something is like acidic or not, right? Okay, so the first thing to do is I would draw out the molecules. So 4,4-dimethyl pentanoic acid. So I would have, so pent means 5, so I have 1, 2, 3, 4, 5 carbons. And that means on carbon 1, I would have a carboxylic acid, and on carbon number 4, so 1, 2, 3, 4, I would have 2 methyl groups. B is formic acid, so formic acid is just has 1 carbon, and then so I can just like draw it like this. I'll like leave out that H. C is 2,2-trifluoroethanoic acid, so ethanoic acid is a carboxylic acid with 2 carbons, and then on carbon 2, we're gonna have 3 fluorines. And then D is non-oic acid, and that has one, two, three, four, five, six, seven, eight, nine carbons, and then it has on carbon one the carboxylic acid. Okay, so what does the word acidic mean? So if something is acidic, that means it's donating a hydrogen, right? So it's donating an H. So it's an H like donor, a hydrogen donor. So if we donate an H, that means that on the atom that the H was attached to, it leaves behind a negative charge, right? Because if we're like ripping this hydrogen off, that means like that lone pair, the bond that was between that atom and whatnot, and like the H would like just like push onto that singular atom. So it's leaving behind a negative charge. So remember that if we're looking at acidity, we're considering like donating a hydrogen, therefore leaving behind a negative charge on whatever atom that like the H was ripped off of, right? And so how do we know if something is more acidic? Right? Because like normally with these kinds of questions with ranking acidity and basicity, you're asked like, oh, is this molecule like more basic? Is it more acidic, et cetera, et cetera. So like, what does it mean if a molecule is more acidic? So if a molecule is more acidic, that means that it will dissociate into its conjugate base form, which is like that molecule with like the minus charge, right? It's like more likely to do that. What makes a molecule more likely to dissociate into its conjugate base form and like H plus, right? What makes it more likely to do that? What makes it more likely to do that is if the minus charge on that molecule is more stable. Okay, so if something is more acidic, that means the conjugate base is more stable. Okay, another way to think about it is how stabilized is the minus charge that you just left behind, right? So like that's what like acidity means. Okay. So now you have to think about like, okay, now the next question is like, what are like, how do you know like what makes a minus charge more stable, right? Like that's like your next question. So there's like many different factors that make a minus charge like more stable, aka making a molecule more acidic. And there's like four main ones, and they're like there's like a ranking for like the importance of them, right? And so I'm just gonna go over like the top three that are like relevant for this like question. And so like the first one would be like what atom is the minus charge located on? So the atom, right? And so to do this, let's like compare three different atoms. Let's compare a carbon that has a minus charge, a nitrogen that has a minus charge, and an oxygen that has a minus charge, right? So if we compare like the like how stable is this minus charge on like each of these three atoms, right? What ends up happening is the direction goes like this. So a minus charge is the most stable on oxygen and the least stable on carbon. Why is that? Electronegativity. So oxygen is more electronegative than carbon. And nitrogen is also more electronegative than carbon, but less electronegative than oxygen. And so because the atom is more electronegative, that means it's able to better stabilize the added negative charge that we just put on it. And so if we add a negative charge onto an oxygen atom, that means like it has it's like it's more stable as like in its conjugate base form versus like a carbon. That's why like you might find it weird to see like a carbon with a minus charge because like you're like we never have seen that like in practice really, right? But that's because like you don't really see it. It's not stable for a carbon to have a minus charge, right? Versus like you've seen an oxygen with a minus charge like many times. You've seen like carboxylate ions, for example, right? And so the first factor that makes a minus charge more stable is what is like its atom, and that has to do with like electronegativity. The second um factor that can make a minus charge more stable is to look at resonance. Okay. So to do this, I'm going to demonstrate like two different like molecules. So I'm going to demonstrate like an alcohol versus a carboxylic acid. Okay. And so now I'm going to like deprotonate these because I'm like trying to look at their acidic form, right? So when I deprotonate these, I get O minus, and then I get a carboxylate ion, right? Okay. So now, when you're trying to like figure out like which one is more acidic, right? Well, the minus charge is they're both on the same kind of atom. They're both on oxygen. So then what do we look at next, right? So the thing about charges is that if you have a lot of negative charge concentrated onto one atom, that's not super stable, right? We want to be able to like spread out that like dense negative charge across the atom, like no, sorry, across the molecule if we can. If we're able to spread out that negative charge, we're able to have a more stable molecule. So with this carboxylic acid, so this carboxylate ion, we have resonance because of this carbonyl carbon, like this CO double bond. We can push one of the lone pairs in and we can push a double bond out. And so the resonance structure that we get is we basically switched which oxygen has the minus charge, right? So in reality, this molecule is like constantly switching between these two forms, right? And so half of the time you'll have the minus charge on this like bottom oxygen, half the time you'll have the minus charge on this top oxygen, right? So that's different than like in an alcohol, there's nowhere for that lone pair to spread out. There's no pi bond next to it for it to delocalize, right? And so with resonance, we think of like delocalizing um, electrons, right? And so that means that in an alcohol, your minus charge is like super concentrated onto like that one oxygen versus like in a carboxylate ion, your minus charge can like spread out. And so because your minus charge is able to spread out, your that makes it more the conjugate base more stable. And if the conjugate base is more stable, your molecule is more acidic. So therefore, an increase in resonance equals increase in acidity. Okay? And and when we say like increase in resonance, we mean by like number of like resonance structures, right? Okay. So then there's another reason for like having um another factor that can influence acidity, and that's called the induction effect. Okay, so let's take two molecules and let's say they are both um alcohols. Sorry, let's say they're both carboxylic acids, right? Okay. Except one of them has um two fluorine groups attached to one of the carbons. And so if we draw the conjugate base, okay, so our first factor that we looked at was where, like, what kind of atom is the negative charge located on? Well, they're both located on oxygen, so that's the same. Our next thing was to look at resonance, and both of these are carboxylic acids. They both have the same number of resonance structures, right? So they're like resonance is like the same, right? So what do we look at next to determine the stability of that minus charge? So the next thing to look at is something called the induction effect. Now, if you have the thing about fluorine is fluorine are an electron withdrawing group. So fluorines are very electronegative, and so they like to hog electrons. And we can think about like they're like pulling the electrons away from like the neighboring atoms, right? That's why like if you see fluorine next to like a carbon, you could create a dipole moment because like your fluorine is more electronegative. It's hogging the electrons more than its other atom, right? That it's bonded to. And so you can think about like the electrons float like are being pulled towards the fluorine, right? So that is good for this minus charge, right? Because imagine like we have like a whole bunch of minus charge attached to this like oxygen, right? And sure we have resonance that can disperse that minus charge, but now on top of that, we also have these fluorines that can help pull away that dense negative charge from like these two oxygens, right? Therefore, if we're like pulling away like minus charge, that means we're like delocalizing the negative charge more, or we're able to like stabilize like that negative charge, right? So it's good to have electron withdrawing groups when you have a when you like have like a huge chunk of like minus charge, right? But now let's compare it. There's like the opposite, right? So similar to there being like electron withdrawing groups, we also have something called electron donating groups. So electron donating groups donate electrons to your um to like its neighboring atoms, right? So an example of an electron donating group are like alkyl groups. So what electron donating groups is like they actually like put more like they can like spread electrons out more over like its neighboring atoms, and so therefore like spread a like minus charge, but we don't want that. If we have like a minus charge already, we don't want to add more minus charge. And so if we were to rank these three molecules from one equaling most acidic to three being the least acidic, the most acidic one would be the one with the electron withdrawing groups. The second would be the one that doesn't add more um, electronegativity to, sorry, not more electronegativity, more like negative charge to its neighboring atoms. And then the final, like last one would be the one that like donates electrons. And so that's what like the induction effect is. But the thing about the induction effect is that like even though it can seem like oh the fluorines are like pulling away a bunch of the negative charge as like from the negative charge, right? In reality, it turns out like if you determine it like experimentally, the values are like less and less and less as you go like each carbon, it's like way drastically less. So induction effect is not as strong as like atom effect or like resonance effect, which is why it's like ranked number three um like in the chart. It's like less important because it has less of an overall result on like the stability of the conjugate base. It still does, and that's why it's like also a factor that influences it, but it's less important. And then finally, the last factor that can influence acidity is like orbitals that has to do with like sp orbitals, sp2 or sp3, but like we don't really get into that with like these kinds of questions that we're doing, so we don't really need to worry about like the hybridization. So like hybridization. But like you can like look into it if you want. The other thing to notice about induction effect is that for induction effect, if we're thinking about acidity, it's like we can think of, oh, we want electron withdrawing groups because we want to withdraw the minus charge. But it's actually the reverse if we were to think about basicity, right? Because what does it mean if a molecule is basic? That means we're leaving behind a positive charge, right? It's like an opposite. It's like we're adding a hydrogen instead of taking it away. So we're adding a positive charge. So if we're adding a positive charge, do we want electron withdrawing groups? No, right? Because we would be taking away electrons from an already electron deficient location, right? So if we're thinking about basicity, we're thinking like actually we do want electron donating groups because we want to like make up for that lack of electrons in that like positively charged area, right? So it's important to think about like similar when you think about like solubility or when you think about boiling point, right? You have to think about like what conditions are you in and not necessarily associate like electron withdrawing group equals good versus electron donating group equals bad. It depends on whether or not you're thinking about like acidity or basicity. It's like important to like consider those factors. Okay. So now that I have all those I like wrote all these notes down, um I'm going to move them out of the way so that I can explain how to actually do the problem. So I'm gonna shift this down over here. Um, okay. Okay. So The first step to doing like acidity and basicity rankings is to, I would say, always draw the conjugate base or the conjugate acid. Um, so like always like draw the conjugate form instead of doing it in your head. So if I were to draw um the conjugate base, like you just look at to see like which site would get deprotonated. So in this case, um, I would have a carboxylate ion. I would have an O minus here, O minus there, and three fluorines, and also an O minus here. Okay, so so the first thing to look at is the atom, right? And they're all the same, right? We have a minus charge on an oxygen for like all four molecules. So that's like the same in that case, right? Um, so that means like you wouldn't really look at the atom being a reason that like the conjugate base would be more stable. Okay. And so the next thing you look at to see is you look at to see is like resonance, right? So in all of these, you like we all have these like carbonyls, CO groups located right next to it. So therefore they're like all the same. Um, they all have the same like number of resonance structures. So resonance is the same. So that means our third factor that we're going to look at is induction effect. And so now we look at to see the like what else we got going on. So we know that like alkyl groups are electron donating and um like fluorine is an electron withdrawing group. And we know that if we have an electron withdrawing group, you'd have it'd make your molecule more acidic. Electron donating group would make your like is um would actually like make your molecule less stable. And so in this case, in C, we have three fluorine groups, so we're able to like withdraw the minus charge more. So that means C would be your most acidic. And then if we look at B doesn't have electron donating groups, so it'd be your next one compared to like A and D, which both have electron donating groups. And now you just have to count like how long the alkyl chain is to figure out like how much like are you donating, right? So we have 1, 2, 3, 4, 5, 6 carbons here, and we have 1, 2, 3, 4, 5, 6, 7, 8 carbons for D. And so therefore, since D has like more, like has a longer alkyl chain, it has like a bigger electron donating group, it's gonna make it less stable. Its conjugate base less stable, therefore making like the original molecule less acidic. But if we look at induction effect, like the difference in induction effect between like A and D, it's like 4.79 and 4.96. So like those two carbons didn't make like the biggest difference in terms of like acidity. And so like that's why like induction effect is like lower than like resonance or um the atom reasoning. But again, like those are like pKa values are values that are determined experimentally. And so it's something that like you would have to like figure out like through an experiment to see like, oh, like what effect has a bigger prominence in determining like acidity and like stability of the conjugate base and things like that. But that is how you do this question. There's two ways to do it. You could have done it based on the pKa values that are given, but in problems where they don't give you the pKa, this is how you like kind of reason out like based on like these different like reasonings, like how do you know if something is like more acidic or not? Okay. This next question is from exam 3, version A. It's question 12B. Um, and so actually this question was changed to say to cross out ethanol. And so actually it was just H2SO4 catalyst, and then there was also like H2O. So like the question was changed, but um we're basically doing like a hydrolysis reaction. And so the way you do this is um, first, right, you're going to have your amide, right? And you have H2SO4 catalyst. I'm going to rewrite that as like H3O plus, but H3O plus, H2SO4, they're both acid catalysts. And so I'm going to draw H3O plus. And so the first step here is that our oxygen is going to rip off a hydrogen. Okay. And so we're going to protonate our carbonyl oxygen. So when we do that, we get this. Okay. The next thing that's going to happen is that now that we have protonated our oxygen, we have now like activated that like carbonyl carbon towards like nucleophilic substitution. So now our H2O is going to come in, act as our nucleophile, and it's going to attack this carbonyl carbon, pushing off the double bond. And so um, similar to like oxygens and nitrogens, like nitrogens can also become protonated too. And so what's gonna happen is like a hydrogen like transfer, whatever. Either like this will happen to the acid or happen like intermolecularly. But the nitrogen will like rip off an H over here. And so now you have a positive nitrogen and you have OH. And so now what this can do is the this N can leave and it'll leave as an amine. And so if that leaves, something else has to make up for it. So like the lone pair will push in to become a CO. We'll remake the CO double bond. And then you have like NH3. Okay. And then now what happens is if you have like you either have like water in solution, you have water in your solution, right? And so you're gonna like regenerate the acid catalyst. And so you're going to have your carboxylic acid. Now, another thing to remember about amines is that amines can also be protonated too. And if you put them in the presence of acid, they will be protonated. That just has to do with like because like the pKa of amines is around like 9 to 10. And so if you have something that's like acidic, right, you're going to be like acidic means like pH is less than 7. And so then like your amines are going to be protonated. So typically you'll have like H3O plus still in there, and your amine will become protonated. And so then you have, so your answer would be, your first species would be your carboxylic acid, and your second one would be NH4 plus. Okay. Moving on to the next question. This is also from exam 3, version A. It's question 13C. And so it says, draw two species that result from hydrolysis of the molecule shown below. So now we're going to keep going like in reverse of what you might like typically have been like practicing to seeing like the acetal formation. So hydrolysis, you have to remember, is adding H3O plus to have some sort of acid, and you also have H2O. And so if you want more practice going over like how the forward reaction works to convert like a molecule with like a carbonyl like CO group into something that is like an acetal, I would watch my exam 3 review video. I go over like the mechanism in like a lot of detail, like going forward and going backward. But for this problem, I'm just gonna show you how you would do it like going backwards, because like that's typically what you have to do if you have to go like in the reverse reaction, because I won't know like what my starting species 1 and 2 is. So the way I would figure that out is to go backwards, right? And so the first thing you would do is I see that, okay, I have oxygens. Oxygens have lone pairs and they can become protonated if I have acid, right? And so if I have H3O plus, what's going to happen is we'll just take this oxygen. This oxygen will become protonated. And then now I have this. right? Okay. And then the thing to remember about like an oxygen with a positive charge that's attached to two things that it makes a good leaving group, so it can leave. And so if this leaves, this like whole big group leaves, something else has to make up for the carbon like that it's leaving behind. And so in this case, oxygen has a lone pair, we can form a double bond. And so I'm going to draw a double bond here. And then we also have our first alcohol species, right? So that's number one. Okay. But now um I have like this positive charge, right? Um, and what do we know about like carbonyl carbons? We know that like, hey, if you have like a positive charge on an oxygen, right, that makes like this other carbon more electrophilic. And what do we have in the solution? We also have water. And so what this oxygen on water can do is it can attack this carbonyl carbon and push off that double bond. And then now we have this, and now we have this. And then if we have something like, again, we have like water, um, that can just like deprotonate this oxygen over here. And so now we have a hemiacetal, right? And so oxygens again can be protonated, deprotonated freely. And so what is a way that we can move forward? Well, this bottom oxygen was like just protonated. So in order to move like forward, we would protonate the other oxygen. So now let's like say we have like H2O plus here. So now this top oxygen can become protonated, right? And so we can draw that like this. Okay, right? And so similar thing to last time, if an oxygen has a positive charge, it's a really good leaving group. And so this whole thing can leave. And then if that group leaves, it leaves behind a carbon, right? That's like missing a bond. And so we have to make up for it. And how do we do that? We use a lone pair on the oxygen to remake a double bond. And so when we push off that group, we get again the same like um two propanol molecule that we like got before. It's like these two are the same molecule, just get two equivalents of them. But the more important thing is to figure out like what's left behind. And so we get this. And then if you remember, like we have water in our solution, so the oxygen can deprotonate that. And then we get our final other species. And so the two species we get are a ketone and an alcohol, and it's these two species. And so the reason why it's important to like draw out the mechanism is because if you didn't draw out the mechanism, you might not have like realized that like, oh, you had another, like you have two like equivalent OH groups, two equivalent alcohols that are formed, so you might have like miscounted your carbons. But if you look at the mechanism and you draw it out, you can see that that is how you get the two species. Okay. This next question is from exam 3, the practice test, question 13A. So it has to do with physical properties. And so in this case, we're looking at solubility. And so the thing about solubility is that we're looking at solubility in water. So increase water solubility um, means that your molecule has to be more like polar. Okay, and so then when we look at that, we look at like H bonding, we look at like polarity, so like dipole-dipole forces, like dipole-dipole interactions, things like that. And that's how we know if like something is more soluble in water. So the first thing I would do is draw out the molecules, and then from there we can like see which ones are like the most polar or whatnot. So two propammonium ion, so I have propane. And then on carbon 2, I'd have my ammonium ion. Heptanol looks like seven carbons, three, four, five, six, seven, and then you have an aldehyde group um, at the end. Heptanoic acid, you have one, two, three, four, five, six, seven, and you have a carboxylic acid on the end. And for D, you have N-methyl pentanamide. So you have one, two, three, four, five carbons, and then you'd have your amide group, and then you also have a methyl attached to the the nitrogen atom. Okay, so now we look at, first of all, can any of these um, H bond? And so the answer to that is yes. Um, so, okay, so we're like asking like which can H bond. Okay, so the ones that can H bond are um, that could be like both H bonds, like acceptors and donors are like A, C, and D. B can only be an H bond acceptor because you have like the electronegative like OH, but it doesn't have like a hydrogen directly bonded to an electronegative atom. Like it doesn't have H bonded to an O or like H bonded to an N. It doesn't have any of these. So therefore, B is going to be the least water soluble. Um, Now, when we look at the remaining like A, C, and D, so the thing about A is that it's also charged. So if something is charged, that's like would be a level above like hydrogen bonding or things like that. It's like super, super polar if it's charged. Therefore, like that would like rank like above H bonding in like polarity or consider. So like A would be the most water soluble. And now we have to compare C and D. And so think about C and D as I can back both as like H bond acceptors, H bond donors. But in this case, you also have to remember that amides have like a resonance form where like if you push, you can make a double bond between the C and the N. So like in this case, like you have your oxygen with a minus charge, and then you would have like N um like the positive charge on the nitrogen. And so because like this is like a pretty like this is like a common resonance form with amides that's like different from carboxylic acids. It's not as stable in carboxylic acid because that require like having an oxygen with the positive charge with the H, right? And so because this is like a like resonance form that like does exist pretty prominently, you're making like this oxygen have like a more negative charge, which is like making it a better H bond acceptor compared to like if you just had a regular carbonyl like CO bond. So therefore, D would be more water soluble than C. So you would rank D above C. So that's the ranking for that first physical properties part. The next question asks you to look at basicity. And so for basicity, we're going to follow a very similar thing to the acidity question, except now we're looking at um, most stable lies like positive charge will equal more basic. Because if you think about like if molecules are basic or not, a basic molecule means that it's getting protonated and therefore it's going to gain a positive charge. And so first thing for A, we're going to draw it out. So 3-methylhexane. So 1, 2, 3, 4, 5, 6. And the methyl is on carbon 3. For B, we have N-ethylpropanamide. So we're going to draw propane and then your amide. And it's going to have an ethyl group and it's going to have a hydrogen. For C, you have 2-hexamine. So 1, 2, 3, 4, 5, 6. On carbon 2, you're going to have your amine. For D, you have 2-propanol. So you're going to have propane with 3 carbons. And then on a carbon 2, you're going to have an OH group. So the first thing you have to do is to draw the conjugate base. Sorry, conjugate acid. Okay. And so the way you draw conjugate acid is that like something has to get protonated, right? So how does something get protonated? So like let's just draw like B, for example. If something gets protonated, like let's say you had like acid or something, you're be like ripping off this hydrogen. And so if I redraw B, your amine would be protonated basically. So your amide will be protonated. And then for C, your amide will be protonated. And then for D, you're going to have a protonated alcohol, right? Now, the thing about A is that there's no lone pairs on an alkane, right? All your carbons are bonded to hydrogen. There's no lone pair available. So A is not acidic at all because there's no lone pair that can even like accept the hydrogen atom. And so that is why I would always suggest like drawing out your conjugate acid or conjugate base because sometimes you'll realize like, wait a minute, you can't even form a conjugate acid for A. It's not basic at all. And so A would be the least basic right off the bat. You know that because you can't even form a conjugate base, a conjugate acid, sorry. So now we're looking at these three, right? So the first thing we look at is atom. And so a positive charge is more stable on a less electronegative atom. And so if we compare, like we see one on the nitrogen, nitrogen versus oxygen. So oxygen is more electronegative and it really, really hates having a positive charge on it. So therefore, D is going to be the next least basic. And so then we have to compare like these two um, forms, right? And so the thing about amides is that amides are actually a little acidic. The reason being is that, as I had just shown before, amides have a resonance structure where like if you like push the N in, you end up with like an oxygen being like negative and you have a NC double bond, right? And so there is a resonance structure where you already have a positive charge on a nitrogen. So imagine that you have now, like, now we have a positive charge on a nitrogen already, like existing in the original molecule, but now you're trying to like protonate it by adding like another hydrogen to it, making it have another positive charge, right? And so like that makes amides not very basic because there already exists a form where like this nitrogen already has a positive charge. Um, and so amides actually are in fact acidic. They're actually a little acidic instead of like basic, which you like typically might think like because you have like a nitrogen, right? And like we know that amines are basic, but amides are actually a little acidic. And so therefore, because of that existing resonance structure, putting already like a partial like positive charge on the nitrogen, that means um it would be less basic. And so that means our most basic molecule would be our amine, which is C. And then the next one would be B, and then third D, and then finally A. And the third part of this question asks us to rank boiling point. And so first thing is I would draw out these molecules. So butanone has 4 carbons, and you have a ketone. 3-methylhexanol, so 1, 2, 3, 4, 5, 6. There is an aldehyde, and then on carbon 3, there's a methyl. On carbon C, it's 2-methylhexanoic acid. So you have 1, 2, 3, 4, 5, 6 hexanoic acid. So you have a carboxylic acid, and you also have a methyl group on carbon 2. For D, you have 3-ethyl 2-pentanol. So you have 1, 2, 3, 4, 5. You have an alcohol group on carbon 2, and you have an ethyl group on carbon 3. Okay. So remember with like boiling point, you're thinking about like a few things. You're thinking about like intermolecular forces with like your hydrogen bonding, your dipole-dipole forces, so like polarity. You're also thinking about like your London dispersion forces, um, right? And then also you're thinking about like molecular weight. Another thing you're thinking about is like branching. So increased molecular weight equals increased boiling point. Increased branching equals decreased boiling point, and increase in IMF strength equals increase in boiling point. So let's look at these three molecules. So first I'm going to count the number of carbons. So you have 1, 2, 3, 4 carbons. in A. You have one, two, three, four, five, six, seven carbons in C in B. You have one, two, three, four, five, six, seven carbons in C. You have one, two, three, four, five, six, seven carbons in D. Okay, so the first thing is I'm thinking like, okay, which of these can like hydrogen bond with itself? And the only one that can do that is C, right? So C can hydrogen bond, making it the highest boiling point, right? Because hydrogen bonding is greater than like or your like polar molecules, right? So D would be the highest. The next thing to look at is um okay, sorry, I meant C. Like, because C can hydrogen bond to would be the highest. The next thing to look at is um like if your molecule is polar or not. And so in this case, we have that that's two pentanol. So we know that A is polar because of the ketone. B is also polar. Um, and like D isn't polar. Or like it is like slightly polar, I guess, because of like that, like the oxygen is electronegative and it's bonded to um actually, sorry, I got it backwards. So actually D can hydrogen bond with itself, so it can hydrogen bond. It's just that for C, you have like your OH group and your oxygen. So you have like two sites of like hydrogen bonding that can exist, but in D you just have like only one. So that is why. Um, so D would be like the second highest. Sorry, I got that backwards. Okay, and then finally, if we're comparing between A and B, um, so B would be higher not only because it has a like higher molecular weight. It has like seven carbons compared to four. Also, like a CO bond from an aldehyde is going to be more polar than it is for a ketone because for a ketone you have like two carbon groups and we know that like alkyl groups are electron donating versus like hydrogen which isn't. So that's also why B would have a higher boiling point than A. Okay. So this question is from exam one, version A. It's question number 7. So it asks us which of these molecules are chiral. And so the first thing that you do is you always draw the molecules. And so 2-propyl octane, you have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then you have 2-propyl. So 1, 2, 3. Okay. And so now we have to ask ourselves, does this have a chiral center? And so chiral means it has 4 different substituents. And so I can see that yes, because we have a CH3, we have an H, we have a propyl group, and we also have a 1, 2, 3, 4, 5, 6. We have a hexyl group. And so this is in fact a chiral center. The second option is 4-fluoroheptane. So let's draw that out. So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, we have a F group. And so I'm going to look at to see what different groups I have. So I have a fluorine, I have a hydrogen, I have a 1, 2, 3, I have a propyl group, but I also have a 1, 2, 3, I have another propyl group. So these two are the same. And so therefore, this is not chiral, not chiral center. Okay, now let's look at the next one. So we have 1,1-dichloro-3-methylhexane. So let's draw hexane. So 1, 2, 3, 4, 5, 6. And so we have a methyl on carbon 3. And then on carbon 1, we have 2 chlorines. So let's first look at carbon 1. So because like this molecule has like some substituents, right? So this one has an H. We have like this whole alkyl group. And then we have a chlorine and we have a chlorine. So this is not chiral because you have 2 chlorine groups that are the same. Now let's look at this center, right? So we have an H, we have a 1, 2, 3, we have a propyl group, we have a methyl, and then we also have like this like chlorine containing alkyl group. So yes, this is a chiral center. Okay. And like all you need is and so like because you have a chiral center, even though you have like another non-chiral center, this chiral center makes the molecule overall chiral. And so because the first one is chiral, the third one is chiral, therefore the correct answer would be only two of the three molecules are chiral. Okay, next question is exam one, version A, question 11B. And so it's giving us these two molecules and it's asking us to um, determine like what is the relationship between these two molecules. And so in this case, we can't assign R and S chirality because if we look at these molecules, they are not chiral. We have two ethyl groups that are attached to this carbon over here. And so therefore, we do not have a carbon that has like four unique substituents, and therefore we can't assign RS chirality for this kind of question. So in order to determine if they're the same compound or not, we have to do some rotating. And so the way I would do this is first figure out a part of the molecule to lock. In this case, I'm going to lock this chain over here. And so I'm going to try and make the molecule on the right look like the molecule on the left. And so first, I'm going to draw out this thing, right? And then like this locked part of the chain. And then I need my bromine group to be like in plane, right? So I'm going to draw out my bromine group in plane to see like what does the molecule look like on the right if I rotate it so that my bromine group is like in plane, right? So again, I would hold up your fingers. So I'm using my right hand in this case. And so my thumb, which would be in plane, would be my methyl group. My pointer finger, which is facing forward, would be my group with my bromine. And my backwards facing group would be my ethyl group. So I want my group that is in the front, which is my bromine group, to be in plane. And so I need to rotate this so that it's in plane. So I need to rotate it like this. So I'm going to rotate it towards me like this. Okay. So if I rotate it towards me, what ends up in front? In front, my middle finger ended up in front. So what was my middle finger before? My middle finger was the thing in the back. So what was the thing in the back? It was the thing in the back was my ethyl group. And so if I trace my ethyl group to see where it goes now, my ethyl group is now in front. So I'm going to draw my ethyl group in front. And so by default, that means my methyl group is now in the back. But if I want to like track where my methyl group goes, I can see like where does my thumb go when I put my group in the front in plane, my thumb gets sent to the back. And so that's how I know my methyl group is in the back. And so as you can see, these are the exact same molecule, right? I didn't switch my dashes or my wedges or anything. So they're actually the same compound, just in a different conformation. We just rotated that carbon. And so for these kinds of questions, I would practice like trying to like rotate molecules. I always like use my hand to kind of like get a better like visual orientation of how these molecules look. Okay, this question is from exam 2, version A. It's question 12C, and it asks you to predict the reactant for when you add HCl aqueous. So, when we add HCl, how did the chlorine get added? So I know it has to have added to a double bond. So this is like an alkene addition reaction, right? And so, um, a chlorine adds to one side, right, of the double bond, and a hydrogen needs to add to the other. So there are different like possibilities for where my double bond could go. So let's imagine a scenario where my double bond existed here. Like could it ex like it can exist like anywhere like attached to the chlorine, right? So it could exist here, there's another one that could exist here and here. So we're gonna like go through the three possibilities one by one. So can a double bond have been here? The answer is no, because look at this carbon, right? This carbon now has one, two, three, four, five bonds attached to it. And that is not possible, right? So it's not possible to have that double bond have been there, right? So I'm going to redraw the molecule, and then we're going to try adding our double bond somewhere else. So could this double bond have been here? Um, so like that means like the hydrogen added to there, right? And so it's like if I imagine a double bond over here, um, we can see that like, okay, this carbon, we have to remember that like for an alkene addition reaction, Cl will um bond to the higher substituted carbon. This is like the Markovnikov rule, right? And so I have to look at like what's like the substituent number of these carbons. So this carbon is tertiary, this carbon is secondary. And so yeah, like that's an option. So you could have um this exist as like a possible like alkene. So what about the other uh, option, right? Can a double bond exist here? No, it cannot, because similar to the first example we did, we have one, two, three, four, five bonds to the same carbon, and that is not possible. So you can't have the double bond there either. So the only possible way you can have the double bond is with this middle alkene over here. So therefore, this would be your answer for like what the original alkene would look like, because that's the only possible double bond that can exist. Okay, this question first from exam 2 version A, it's question 12D, and it's giving you an alcohol, and then it's asking what would happen if you performed a reaction at 180 degrees Celsius and you are adding like an acid catalyst. So the thing to remember about like H3NO is that it's just like an acid catalyst, so you can rewrite it as like H3O plus, right? 180 degrees Celsius is high heat. And so the thing about this reaction is first I would look at like what kind of alcohol is this? It's a tertiary alcohol. So if we have a tertiary alcohol and we have high heat, we perform a dehydration reaction, aka like an E2 reaction. And so we're going to do like an elimination reaction. And so therefore, like we're removing the OH and we're forming like a double bond, right? And so you'd form a double bond like attached to the carbon where the OH was. And so I can either form a double bond here, or I can form like to this carbon. I have the double bond there, or I can form it here, right? And so the difference between these two is like one of the alkenes has four substituents. The other alkene only has like one substituent, right? So the thing about like predicting like which would be the major product and which would be the minor product, their major product would be more stable, and then the minor product would be less stable. And the thing to remember at alkenes is that alkenes, like increasing the number of substituents on an alkene increases their stability. So therefore, the major organic product is going to be the alkene that has more substituents, which would be the one that has four. And then our minor product would be like the one that only has one substituent. And that is how you do that question. And so that is all I have to review for the final. A lot of it was focused on some of like the earlier content went over in this class. And so if you want more review on content from like the later half of the quarter, I would go watch again my like exam 2 review video and exam 3 review video. I go over like a lot more of the mechanisms and things like that. And yeah, so good luck on your final.